from Cryogenic Engineering Center. Presently, he is working as a visiting professor in Department of Physics at IIT Kharagpur. His research areas include superconductivity and applications, quantum computing, vacuum technology, cryogenic engineering, semiconductor engineering. He had served as head of Cryogenic Engineering Center and chairman of the Hall Management Center, IIT Kharagpur. He is a fellow of Indian Cryogenics Council, senior member of IEEE, and life member of Indian Vacuum Society. He had visited Germany and France for advanced training in vacuum and cryogenic technologies. He had served as a consultant to Power Grid Corporation of India, Bharat Heavy Electricals Limited, DRDO, Crompton Greaves, Schneider Electric, and Applied Materials. He had handled sponsored projects from government agencies like IPR, DST, CSIR, ISRO, and reputed industries. He had organized 35 short-term courses on vacuum technologies and process applications. He had co-authored a book on vacuum science and technology and contributed book chapters on superconducting energy storage. He had published 110 papers in reputed international and national journals. He had guided 10 PhDs, 2 MS theses, and 35 MTech theses. He had delivered Swayam NPTEL course on vacuum technology and process applications. He is a technical advisor to National Design and Research Forum and various industries. We are very fortunate to have you in this virtual platform, sir. Sir, I request you to please share your valuable knowledge with us. Please take over the sessions. Thank you, sir.
Thank you very much. Welcome to all. First of all, I really give thanks to Gates Institute of Technology for giving me this an opportunity to interact with all of you. It's my pleasure. And the topic given to me is vacuum-based thin film deposition units, which is a typical solid-state thin film physics type of topic. And I thought it will be quite useful to all of you because it is all advanced materials processing workshops. So nowadays, advanced means something which is immediately useful to all the public at large. And all of you know the most useful things are the one that we are now watching, that is the laptops. And then after some time, what we will watch is the digital TVs. Then, of course, mostly watched, mostly used material device is called cell phone. So these mobile phones, if you go inside the details of it, most of them are manufactured, all of them, all three, that is mobile, laptop, and TV, and several other control circuits, even in our washing machine or freeze or anything. All these things are heavily based on solid-state thin film devices. They may be in the form of sensors, they may be in the form of circuits, they may be in the form of logical operations, so and computational things, and varieties of control systems in power systems. So entire gamut of all the applications in our day-to-day life, starting from the morning breakfast up to the night going to bed, everywhere we require a lot of electronic devices which are highly dependent on semiconductor devices and metallic devices and dielectric devices, components, varieties of resistors, capacitors, but all of them are in a microscopic scale. You can't make a big capacitor or big inductor or big resistor or big diode, big triode. Gone are those days. There were 100 years back, we started doing valve electronics, and 60 years back, first semiconductor has been manufactured and PN junction has been made. That time, nobody was knowing that it can be useful to such a level that in 1 square inch of a thin film wafer, on the top of a silicon wafer, you will have millions of circuit elements. So that is the level of micro miniaturization. That's why the processing at that nano scale is considered as advanced processing. And processing different varieties of materials like dielectrics, semiconductors, insulators, and inductors, resistors, capacitors to form different logical circuits, computational circuits, sensor circuits, and useful controllers, etc. Definitely, these involve advanced materials and also processing at nano scale. And one trying to do the guarantee of this circuit is very important. That's called reliability. So we have to characterize these things thoroughly to give a certificate. So that if 1 lakh phones are made, almost 1.01% should be rejected. All the other phones should work. So reliability should be high. For that, we have to characterize each device perfectly so that it is going to work for the purpose for which it has been manufactured. So the processing, which is the other name of manufacturing, in a nanoscale or a microscopic scale or an advanced scale involving different advanced materials with perfect characterization, is an extremely important topic. It's very good that Department of Physics, I think the Gate Institute has taken the initiative in organizing this conference. So I thought my topic will be useful because, first of all, world is going to smaller and smaller gadgets and faster gadgets. That means I should be able to keep all my necessity in a small chips, small bits, a small cell phone, small TV, small thing, everything, small capsule. Okay, everything should be small and beautiful and reliable. Second is, it should be very fast. Within 1 second, I should be able to book my ticket. And within half an hour, I should be able to travel. So lots of new things have come. Whatever is happening to us, it is also happening to materials. Materials means electronic materials mostly. Because the electrons inside the material also should be very fast traveling. And the component should be very tiny, minimum dimension using VLSI circuits. So electronics people definitely know it. So entire technology has come to a digital world with microelectronic things involving advanced materials with proper characterization. So how to do this? Best way is a three-dimensional object. You try to make it into first two-dimensional. So one dimension is already less. That is called thin film. Then use scribe horizontal and vertical into different pit cells. That will be called LSI. If it is a large scale, very small things, then it's called VLSI. Okay, advanced VLSI, very large scale integration circuits. So whatever it is, first you have to bring it from three-dimensional to two-dimensional, and two-dimensional using VLSI circuits to one-dimensional. And from the one-dimensional, if you want to go to quantum effects and quantum computers, future computers, to do most complicated operations in a fraction of a minute, then we need to go to almost zero dimension. They are called quantum dots. But all of them have to be physically made by some advanced materials. Okay, dielectrics, superconductors, semiconductors, and insulators, and magnetic materials, ferroelectric materials. With proper characterization right from the beginning in the process of making that material into the final shape of a sensor or a circuit, every step, perfect control is required. That control will not be there if there is an impure atmosphere and we are trying to process it. So it is very important to have a clean process. Clean and green is the word of present day world. If you do not have clean processes, when you are trying to dope PN junctions with parts per million, and before that some oxygen molecules or whatever is there here in the even hundreds parts per minute, million type, they get deposited, then we don't get the PN junction in the way we want. So PN junction reliability depends on the contamination of otherwise contaminating molecules which are floating around in the atmosphere. So we need to have a perfect vacuum chamber. So it is not only important to reduce the dimensions from 3 to 2, 2 to 1, 1 to 2, 0 almost. It is also important to realize these circuits, elements, components using a very clean technology, clean rooms. And best cleaning environment is called vacuum. So I have chosen a topic that vacuum based environment for two-dimensional thin film deposition, which will be further converted into one-dimensional by VLSI to realize various useful devices, which all of us know, called mobiles, laptops, and TVs. Am I clear? Anybody? How many? Of course, I can even ask because all of you are like students. So, would you get a feel of what I'm talking? If you want, I can repeat. But otherwise, have you understood the importance of vacuum-based coating units or deposition units? Coating is normally given to a thick film, like our watches, etc., gold plating, etc. When you go to very thin films like 500 angstrom, 1000 angstroms, with a continuous deposition control of 1 angstrom per second, we are talking. That is the level of advanced material processing possible in vacuum technology using various thin film deposition technologies. That is the what you call necessity of the present day. That's why I have taken this topic. So vacuum based coating unit is nothing but deposition of a two-dimensional film on a surface in a vacuum environment. This I have explained now. Now they have got several engineering applications which I already told you in public life. Okay. Can anyone tell the vacuum based advanced material processing is important in devices like, can you fill the gap? What are those devices which require vacuum based thin film deposition? Can someone give me a feedback? What are those devices which you are using? Can anyone tell? Shiva? There is one-way communication. Otherwise, can you tell that two to three devices which you are using vacuum-based thin film deposition? What you are using in day-to-day life? Because I want the lecture to be little interactive. Otherwise, I will be keep on talking whether you are listening or not. I really do not know. So I just want that is my style. Okay.
Sir, this is the live in YouTube session, sir.
Okay.
So
There
me
will
and
not
me
be
only for in this session in the Google Meet, sir.
Oh, okay. Means what?
Sir, will the participate any questionable query?
Yeah.
Post in chat box, sir.
Okay.
After end of the session, I will ask the
Okay. No, right now I can interact with you. You can simulate. You are also like a student, no? So that's why I was typing. Okay. Anyway, I understood the point. So let me complete the lecture. As he's rightly pointed out, we can get the questions if there are anything. Okay. So these are given in the second paragraph. They are called laptops, mobile phones, LED TVs, coated spectacles, solar PV coatings, solar thermal coatings, diamond coated machine tools, decorative coatings, and coatings on household items like utensils, packaging materials. So you can understand. No, don't shift the slide, please. When I say next slide, you shift it. Okay. So these are the day-to-day things we are seeing. They all have some coatings, deposition, thin films. Why thin films? If it is too thick, then we are not getting any advantage. We have to minimize the dimensions. Then only it is called small scale, minute, or what you call very, very handy. That is possible only if you reduce X, Y, Z dimensions. So a thin film already Z dimension is reduced. By VLSA techniques, you can make it into that very, very small scales. So that way X, Y also we are playing a game so that you will get a minimum to minimum circuit, but it works like a typical solid state electronic circuit. So it all depends on our way of thinking, whether it is a communication technology, whether it is a computational technology, whether it is a sensor technology, whether it is a decorative technology, whether it's an entertaining technology or packaging technology, the level of complication, the level of sophistication will change. If it is a high speed, 500 megahertz speed or 1 gigahertz speed processor in a computer for making high speed calculations, naturally the sophistication has to be very high. the thin films have to be deposited in a vacuum environment in a layer-wise, atomic layer-wise. If it is only a small coating on a bangle coating or something, it is enough even if you produce a poor vacuum. There also vacuum is required, but not a high quality vacuum. Even if little bit impurities are there, it doesn't matter. The cost of the item itself is few rupees. No, it doesn't matter. We cannot afford to have a sophisticated technology. But when you go for multiple production in a fab, fab nowadays semiconductor manufacturing has become a big national mission program of our country. So definitely all of you, if you are interested, if you understand these things properly, if you are working as a teacher or somewhere in the student, you can get a lot of benefit in getting the research projects. Okay. Okay, so several industrial products also, apart from these microscopic electronic products, they are called wear resistant materials. They are also thin films, but thick films, but basically films. And corrosion resistant, something is corrosing. You make a film of some other material which does not corrode. Then it will act like a protective coating. And thermal resistance, the heat transfer will not be there. Or electrical transport, you want a metal table, but on top of it, there is an insulating table so that you will not get shocked. So that sort of coatings are also available. Optical coatings to make it efficient. If you are traveling in a car, the reflection should not fall. It should reflect from the front end itself, but it should not enter into your eyes. So there are anti-reflection coatings and anti-transmission coatings. Varieties of things are there. So we'll have to see how best we can engineer these materials with proper characterizations in thin film method, so that you will get the required behavior of the final device. So vacuum environment gives very good advantage for this thin film process by reducing the contamination first, and also since vacuum is low pressure, whatever we are trying to evaporate and prepare a thin film, because thin film means what? From a bulk we have to melt, make it a liquid state, make it a vapor state, and then gets deposited. Like in agarbatti, when you are trying to heat, the vapor comes, and if you put a hand, you will get a thin film. So that's the technology we are going to work on it. So, but heating requirement also will be saved, because we know in our class 10th level that as pressure is reducing, the boiling point of a liquid decreases. Melting point and boiling point. Melting point is not such sensitive function. Boiling point is definitely sensitive function. So once, for example, some material is more melted, and it will not evaporate immediately if it is in atmospheric condition. In fact, it gets contaminated. But if it is under vacuum condition, the pressure above that liquid is so small that it is less than the saturated vapor pressure at this temperature. So molecules will evaporate easily. That's why vacuum reduces the boiling point, thereby saving the heating requirements and operating temperatures, and also power saving, and increases the time to form monolayer. Because impurities, if they are coming, if it is ultra high vacuum, the impurities will not form a monolayer. Before that, your thin film is formed. Monolayer formation by impurities is a defect, whereas monolayer formation in a controlled way, atomic layer, by your intentional process called thin film deposition is the requirement. So you will have to see how to reduce oxidation, how to reduce contamination, and how to make thin films in a perfectly controlled way, so that whatever atoms are getting deposited, they readjust and mark a crystalline film. And if required amorphous also, you can make it. All those technologies, if you properly optimize, you will get quality thin films under vacuum conditions for realizing all modern gadget devices. Next slide, please. Next slide. Yeah. So you can also go through this material at your leisure, but for your convenience, I will also explain little bit. But it's all very simple things. But sometimes simple things are difficult because you are not thinking it as a simple. Okay. So vacuum coatings are broadly classified into two types. Physically, you evaporate. That means you take ice, for example. You melt, then water, then you heat. It will become vapor. It is true for metal. It is true for everything. Every material has got a melting point and boiling point. Okay. If you do physically, that's called physical vapor creation, that vapor gets deposited to make a thin film under a controlled vacuum environment so that contamination is reduced and control is faster. So molecules, when they are coming from the melt, when they are evaporating, they don't evaporate like a vapor, though we call vapor physical vapor, but they vapor like a molecules, because lack of time I will not be explaining the concepts of mean free path, etc. The molecule to molecule distance under vacuum condition is much more compared to the distance between the substrate and the source. That's why each molecule of the vapor molecules will get deposited. The control of these films to make different CMOS devices or insulators in a micro scale is very good. If you are having a slow and steady depositions, then you will have a perfect control to make the lithography patterns and to make the ion beam deposition, all the processes slowly to make different thousands of transistors and diodes and the lakhs of resistors, capacitors, and put all these active and passive components into a circuits and digital circuits and make some AND gates or OR gates or NAND gates out of those circuits, semiconducting circuits, and use those AND gates, NAND gates to realize certain logic things by making a different 0101 type of signals, which in a machine language and a simpler language, and finally convert into a English and thereby programming, software, everything. But finally, some hardware has to take place. The computer is a hardware, but what we are giving instructions to it is only a software. So the hardware depends on very high quality deposition things, on physical vapor depositions. If you do not want to melt and evaporate, you can take some chemical vapors already produced in a chemistry lab. Now I am going from physics department to chemistry department. Those vapors will mix and produce third material. Okay. At some operating temperatures. Chemistry people definitely know every reaction requires a particular temperature, particular concentrations, mole fractions, etc. So if you try to take the chemical things in the form of gases into a vacuum chamber through a walls and maintain continuously equilibrium vacuum by running the pumps, vacuum pumps, which I am not explaining here, but some other day we will explain vacuum technology separately. And that way, the chemical vapors will deposit and you will start getting semiconducting thin films. This is called chemical vapor deposition. And if you assist this chemical vapor deposition by putting plasma instead of molecules, they will be formed into ions. Ions can be easily transported to make the different structures, and they can be etched through ion beams, ion beam etching. All these processes, semiconductor manufacturing people know definitely. But that's also thin film. But it's only chemical vapor deposition assisted by plasma. Plasma enhanced chemical vapor deposition. Okay. And sputtering. It is like scratching the materials and depositing instead of evaporating. So, for example, if you go to agarbatti, you are heating it and evaporating. That is called thermal evaporation. Physically, where you are creating vapor. But if you go to some temple and you try to scratch some molecules from that Shiv Mandir and then put it here, that's also thin film. But you are not melted and evaporated and put your hand there and getting deposited here. You are only trying to scratch it. That process is called sputtering. But you cannot scratch atoms. You can only scratch thousands of atoms like specks of molecules. But if you want to scratch atoms, you have to use a sputtering technique by ion beam tools. Ions can be actually like a machine tools like our hands, and they will scratch and evaporate it. That is called sputtering. So physical vapor deposition, chemical vapor deposition, and sputtering. Similarly, you can put an electron beam, that is a cathode ray beam, with an intense beam generated by thermionic emission, and then try to get it deflected by electric and magnetic fields, focus it on a particular spot. Then that spot will be very hot, remaining material will be very cold. It is like laser surgery of our eye. Same laser beam or electron beam. Anything hits. In eye surgery, it is laser beam. In depositions, it is a laser electron beam. Any beam, intense beam having thermal energy, it hits. But your eye does not know. Your eye is totally cold. But laser is hitting there. And that spot is getting evaporated in surgery. It takes. So spot temperature, our sensory organizations do not realize that spot is melting. Same thing here also, that spot will melt because of electron beam. So thin film deposition units have got different ways of doing it. Physically evaporate it by thermal technique, chemically mix two vapors and create a third vapor of our interest, and enhance that chemical vapor deposition by plasma. so that instead of vapor molecules, there will be ionic molecules, or sputtering by scratching, or an electron beam focused and melting locally without knowing the surrounding 199.99% of the same material does not even evaporate, only spot evaporates. That many molecules are enough. Like that, like a big uh, bowl, you only take a little bit of chutney, like that. The small amount is melted. That is possible by focused ion beams, focused electron beams, focused laser beams. So broadly, physical vapor deposition and chemical vapor deposition, but the tools that are used in physical vapor deposition can be a simple heating, electrical heating by resistive heating of a board, or it can be an electron beam, or it can be some other beam. So this is what I have explained. Very high melting points, you cannot electrically heat and do it. You will have to do with some other materials like electron beam depositions, etc. So while you are doing this, you have to parallelly, you control the deposition technology. How much thin film is getting deposited? 1 angstrom per minute, 10 angstroms, then 100 minutes are required to deposit 100 angstroms. But if you deposit 100 angstroms per minute rate, then 1 minute you will get it. But the quality of that film may not be good. So layer by layer depositions, they are called popularly molecular beam epitaxy layer. Basically, it is also thin film deposition. But the level at which sophistication and slowly you are depositing to get a high quality for the modern devices, that's called molecular beam epitaxy. Otherwise, it is a thermal evaporation. But instead of evaporating, melting and evaporating, even from solid itself, you can sublime by heating. That's how molecular beams use a cells called effusion cells. Without even melting, you will get some vapor. Even solid has got vapor. My hand has got a vapor. But I don't feel much. It is so low vapor pressure, it is suppressed by these molecules. Okay. So it all depends on the level of sophistication that is required. In chemical vapor depositions, there is no hot surfaces or anything. It is only thermal decomposition by the chemical reactions. Okay. So it is already in vapor phase, that is admitted into the vacuum system. To deposit, you can have little thermally excitation or plasma excitation, you can do it, but to make it to appropriate temperatures with or without plasma. These are routinely used in semiconductor manufacturing in making the chip designs and IC chip manufacturing that we are using in cell phones, mobiles, laptops, and TVs. Okay, so they are very useful thin film deposition technologies, both physical vapor deposition and chemical vapor deposition. And metals, say alloys and semiconductors, everything can be deposited. It's only a time of the technique of deposition. Okay, please go through these things separately, because I don't want to read the same thing. And if you read, you will be able to understand after listening to this. Otherwise, in Wikipedia, if you highlight these words, you will get a lot of information. So this is the way the classification of deposition technologies are there, but all of them are requiring vacuum for two purposes: to reduce the contamination, to make a fine control of layers of deposition. Okay, both are very important. Then only you will get crystalline films. You can have bulk solid crystal, but if you want to have thin film crystal, your deposition should be strong. Otherwise, lots of hills and form there, they will be polycrystalline film, which will not have electron mobility to so fast that it will go to 500 megahertz speed. See, you are doing so 500 megahertz or 1 gigahertz means every nanosecond electron is going from one side of the chip to the other side and doing an operation, whether it is a logical operation or a switching operation, 0, 1 states, switch over, etc. These are all done physically, what we are going to do with the software. Okay, so this level of sophistication is possible if you are having all the gates from which you are making the digital circuits. They are manufactured out of semiconductor circuits, which are manufactured out of thin film, proper VLSI lithography techniques used. Then you will get all those microelectronic chip manufacture. So thin film deposition technology is the first step or a third step. In between now and then we use again for interconnects, making the connects to the external world so that you can put the chip in the control board and those other things are simple power supplies. So in a motherboard, the most costliest part of the motherboard is only chip. Remaining parts are all not much. Anybody can assemble. Any country can assemble and prepare a laptop. But very few countries have got the chip manufacturing. Today, India is going ahead in a very large scale. A lot of money is being given from the government also. They are encouraging it in schemes where even in private engineering colleges, any universities, many people are trying to get these projects and trying to make their own contribution of either in a solid state or liquid state or vapor state depositions or controllers or electronic circuits or measuring equipments or characterization. Any one of these things, if you try to do it, you will be able to produce PhDs or MTech thesis and train the students properly. And also you will get a lot of money in the form of sponsored research, industrial consultancy, etc. If I have been doing the same thing, you can also do very easily. Okay, so device manufacturing starts from vacuum deposited thin films. Is using several techniques called physical vapor deposition or chemical vapor deposition. Having understood the importance, having understood the classification, having understood already what is the meaning of different deposition technologies, those technical points, already I have explained. So I will be showing the same thing again in the next slide, only in the form of figures. There I will not talk much. I am already briefing you in a popular language to you so that already you know what it is, what is sputtering, what is electron beam, what is laser beam, what is thermal evaporation, what is chemical vapor deposition, what is plasma enhanced, why vacuum is required, why contamination should be there, not be there. Because when you want to have parts per million P-type, parts per million N-type, if it is crossing, the device will not function as you want. And if the PN junctions are not properly maintained, or field effect transistors are not properly manufactured with particular perfect doping, you will not get proper transistors, proper CMOS, proper gates, proper circuits. So thin film, if it is pure with VLSI, the small pit cells will be poor. And if you dope properly under vacuum, and that will be very nice. And then deposit metal layers to take the external contacts, they will also be good. So every process, vacuum has to help, thin film has to help, but in an atomic scale. If you try to do it, at the end, you try to put it with a chip, close it, but make a little bit macroscopic legs. But this, even if you push, you cannot push molecules and circuit will be spoiled. That's why it is all impregnated properly. That is called the semiconductor packaging. Circuits are packaged. The outside legs are normal things. You can put it, and if you are making a mistake, even if it gets bent, you can again bend it like that. So to bring it to that level, several processes are there, and every process has to be characterized in situ. In situ means same time when you make it process. Don't test it after some time when you realize that it's not working properly. So these are all interrelated parameters. Next slide, please. Same thing I am giving here. Applications I have only listed, and deposition techniques I have listed. And bottom I have given various rotary pumps, diffusion pumps, roots blowers, and vacuum measuring equipment as additional information, because in the actual thin film deposition units, you will be using a vacuum chamber. You will be using pumps to remove. You will be using some control valves to let in gases. You will be using some electrical fluid throughs to pass the current or plasma realization. Or you will use some flow controllers to control the things. These are the equipment required in the bottom I have given. And right side I have given possible applications of these thin film technologies in optical, display, semiconductor. Display technology is a very big thing. I forgot in the beginning. This YZ plane of our laptop is display. The XY plane is semiconductor. This is called semiconductor device, and that is called display device. Both of them are requiring thin film depositions manufactured under ultra high vacuum conditions, later made it into small elements by VLSI and doped properly and sealed properly, metallized properly, controlled properly. Then only you will get display device as well as the semiconducting device circuits with logic gates, so that we can perform our operations on computations, or we can also use them in their electromagnetic way to the remote sensing, or as well as communication technology. We can use our same circuits in our controlling our day-to-day device like washing machine or any other thing, or even the sensors that we are seeing here. They are also thin film sensors for making the surveillance in warfare, etc. So these are the methods, these are the applications, these are the equipment. I just want you to go through 1 minute, all of you, before I switch over, because otherwise you will forget what I have told. So I am just taking 1 minute rest intentionally by closing, but by showing the, please keep the slide on. Let all the participants see the slide for 1 minute. Then I will come back. Okay. So assuming that you have understood all it's talking in film processes, deposition processes, and their characterization. Now I will show you how they physically look like. Next slide, please. There are so many varieties of systems. Even chemical vapor deposition I have explained, but in literature you will get. But since lack of time, I'm not going into details of that's a big field by itself, CVD. Though I have explained already in the first 2 slides, I wanted to take some examples of physical vapor deposition. So in laboratories, and you don't require a very high-tech fab facilities like industrial facilities. These things you can realize it right in your laboratories. That's why I taken these examples. But if you are interested later, I can talk on chemical vapor depositions and various modern technologies, mixing all these deposition technologies with characterization facilities in the large scale industrial scale, and how to plan power, what are the power requirements, what are the water requirements, and clean room requirements, and basic infrastructure. All that I have my own lecture series available. If you are interested, some other day we can discuss. Today we will confine ourselves to the thin film deposition. So in this slide, what you are seeing, concentrate on the first thing, thermal evaporation. Okay, you can the cursor, you can take it to the thermal evaporation. Figure 1A. Okay. Say there you will see there is a boat, very small thing, boat, that is getting electrically heated by a power supply from the base plate of a bell jar. That bell jar is continuously evacuated by a vacuum pump. So what you are seeing here is a vacuum pump connected to a bottom. The pump I have not shown, but it is connected to vacuum pump, and an electrical power supply passing through a electrically insulated feed throughs, because bottom plate is a metal plate. If you send directly, it will be short circuiting, but there are some insulators through that it will go, and on that there is a small board that is getting heated because of I square R, and heat transfer is not taking place because entire bell jar is in vacuum condition. Convective heat transfer is not there. Conductive heat transfer little will be there, and radiation we cannot avoid. But main convective heat transfer is not there. So with little bit of electrical power, the body gets red hot. But it will not get oxidized because the vacuum pump is removed all the air. Now, in that, a small red colored blob is shown. That is the material, whether it's a copper for metallization, metal films, or a silicon for semiconductor films, or insulator, whatever you can put there. That will be melted, and that evaporation takes place. The 3 arrows are showing as a metal vapor. I have shown is a metal deposition. It is equally valid for semiconductors or any other material. If it is a ceramic material, you have to increase the temperature so high. So we will do some other technology like sputtering that I will explain later. But otherwise, in principle, this technique works for any material. And where these evaporated molecules are going? Towards a place called substrate on top, which is supported by a back plate. Substrate can be a glass plate. If it is optical things, it can be silicon wafer if you are depositing P-type, N-type, etc. So these molecules will go, and these are all very hot molecules. When they go all the way there, it gets deposited like thin film, and it is a huge thermal mass. It will be cold instantly. Instantly, it will be cooled. Otherwise, you can pass some water circulation also there, and it gets deposited. Okay, like when you take agarbatti, it's very hot here. If you touch it, you will get it burned. But when the vapor comes, and if you keep a substrate, this is called hand, a black color thing will be deposited. Is it not? So here it will be cold, but here it will be very hot. These are called vapor molecules. But if you keep the entire thing under vacuum, the vapor will be discontinuous molecules. Then that's called molecular deposition. And that's what is shown in the molecular beam epitaxy in the bottom figure. Bottom, there is one molecular beam epitaxy. You can highlight there. Bottom, forget about that. Come to the bottom, figure 1C. Figure 1C. That's called molecular beam epitaxy. But it's also thermal evaporation. But here, the pumps, UHV pumps are used, not small pumps. There are UHV pumps, Patran pumps, cryo pumps, turbo pumps to produce 10 to the power of minus 10 tar. See, this atmosphere is 760 tar. If you want to produce ultra high vacuum 10 power minus 10 tar, you will have to use sophisticated vacuum pumps. That's called vacuum technology, which is a background support of the thin film technology. Thin film technology is a background support of VLSA technology, which is a background support of computer technology. Okay, so now instead of melting, there are effusion cells are there, two cells type thing. They are looking in the bottom, and from there vapors are coming. They are joining on a substrate which has got X, Y, Z tilt rotation. That means you can keep the substrate like this. You can mean free path of the molecule. After what is vapor? Vapor consists of molecules. Now in the atmospheric pressure, the distance between the molecule is submicron. So we'll think it as a gas. But when you go to the ultra high vacuum, the distance between the molecule is of the order of 100 meters. Then it is not called gas. It's an ensemble of molecules. It's a group of molecules. Okay. So for example, when a lot of cows or birds are there in one place, it looks like a big carpet. But when the sky, they are looking like individual birds. So same thing here, when the distance between the molecule is very high, when it will happen? Under ultra high vacuum conditions. Because as the vacuum improves, rarefied gas density has come down. So molecules for the same volume, number of molecules are less now. So they will be freely moving. That's called free molecular region. Instead of gas, they go, but they will go in the straight path. The bottom, you are giving heat and asking the molecules to flip, go. And when the molecules are going, 100 molecules of gallium and 100 molecules of arsenic, if you put, you will get 1:1. If you molecules of gallium, 40 molecules of 1:0.5. The thin film formed will have a chemical composition dependent on the molecular fluxes. And air chamber is controlled. If you want some lead-in, intentional gases can be leaked in through a gas inlet to make some oxide films. Sometimes you require oxygen. Some oxygen is an enemy if you are depositing metallic thin films, because metal should not get oxidized. But if you want to insulate area, you have to have silicon dioxide. That time oxygen in a controlled manner without disturbing much of a vacuum level. Some molecules are deposited. They are very highly controlled walls. And every time, whatever we are trying to do, the thin film is getting formed. That will have X, Y, Z tilt rotation. Why you require such what you call degrees of freedom? So that you can show it to different sources if you want, by putting shutters. All that I have not shown here. And you can keep it once here, once there like that. That means a series of multi-layer depositions. You can do that. An entire chamber is having one vacuum gauge to measure the equilibrium pressure on the top of it. And there is one RGA, that is called residual gas analyzer. What is this residual gas which may impurify our actual process? You must know. That is called black box. Whenever accident takes place, black box will tell why this is thin film, why this semiconducting CMOS FET is not effective. That's called quality control. Then reflecting high energy electron diffraction, that's called RED, that will measure whether the quality of the film on the substrate on the top is it crystalline or polycrystalline. So with all these pumps and RED and RGA, gas inlet manipulators and gauges, the entire chamber is connected to a vacuum pumps. And right side with a gate wall, gate wall, it is connected to another chamber called analysis chamber. So you manufacture, send it to analysis chamber and bring it back again. If it is not satisfactory, throw it. Otherwise, you make one by one, you start making IC chip 1, IC chip 2. Lakhs of chips have to be manufactured because 100 crore population, 100 crore cell phones, and circuits have to be manufactured. So multiple circuits are there, multiple chambers will be there, and each of them have to be analyzed whether this will act like a cell phone or not. So analytical chambers will tell XPX, XRD, and various other things. It's chemistry, thin film that is deposited, that will be further subjected to the VLSA technology, and it will be further subjected to metallization and lithography and doping, physical P-type, N-type, and realizing PN devices against devices, and try to realize whether PN devices really happened or not. You have to, on the spot, in situ, you have to test it, analyze it. That's called analysis chamber. So entire all these things together is called a semiconducting IC chip manufacturing for all our elements. And if you put a typical semiconducting manufacturing facility by Google or IBM or anything, you will see a very sophisticated thin film coating unit. And all the people who are entering and manipulating all these things, they should vary their separate. They should not go with these hands because moisture will contaminate. We should have gloves, we should have everything closed, and there will be oxygen inside, but that should not come into the room. These are called clean room requirements, etc. That's an altogether a different game, and the semiconductor manufacturing. If you some other day I will discuss about it. So that is called physical vapor deposition. This is same physical vapor deposition done under ultra high vacuum conditions to slow the process beam wise, molecular beams. Epitaxy means small layer, atomic layer, one atomic layer. This is called molecular beam. So these two are interrelated basically. This is in high tech, that is a low tech. That is the top thermal operation. You can make it in 1 lakh, 2 lakh rupees in your lab. Bottom will be more than 4 crore, 5 crore rupees because it's ultra high vacuum. Pumps are costly, chambers are costly. They should not be leak into the vacuum chambers. If there is a flaw or welded joints leaking or bolted points, if there is a leak, air will be continuously going in because inside vacuum, outside atmospheric pressure. So, like this physical chemical vapors, in chemical vapor deposition, instead of beams and heating, etc., there will be two gas inlets like the one we are showing in the MBA, that I am not showing in CBD now, but that is same chambers. Some pump will be going on, some gases will be coming, some heaters will be there, and chemical vapors are deposited, a reaction takes place, the third gate will be realized. So reaction, if it is there, that is called CVD. If it is only a phase change, it is called PVD. And there are high melting points. You cannot operate these technologies for thermal, etc. That time, laser beam deposition is used. In laser beam, that is also called a vacuum chamber. That also has got analysis on the equipment. They will be there. I have not shown here because they are common equipment. And they will also have vacuum gauges, etc. Instead of heating or anything, you make a high voltage between the source and the substrate. Thin film deposition means the material will be in bulk from the source. It will be deposited as a film in the substrate. The piece that is holding the film is called substrate. The piece that is there holding the bulk which is to be deposited, that is called the boat or something. Whereas in laser beam deposition, the material to be deposited is a disc. It is connected and applied to a high voltage and properly cooled. That is in the left side. And that one laser beam is falling. And there is a flue, that is a small glow-like thing will be there, plasma gold like thing, because of laser beam. And this hot vapor molecules are coming from the surface of the blue colored material, and they get traveled, and this is heated instantly. Only spot of the disk is heated. Entire disk is at room temperature. Only a laser beam from the top, you see, beam is falling and instantly depositing that film. A small micron here can form a 1 meter square film here, because this thickness is less. Okay, so material is in microscopic here. Density is very small. The width is very high in thin film, but the film thickness is only angstroms. So total volume of the material is not much. So that way, in the right side, the substrate holder will be there with suitable attachment, and that gets deposited. That is called laser beam deposition. I have explained everything in this slide. I hope you will be able to read and understand these things. I will give 1 or 2 minutes to understand thermal evaporation. Same thing under high vacuum conditions without melting, but the solid itself you can generate vapors and beams. And because mean free path under high vacuum condition is so large compared to the distance between the source and the receiver, if that is more, molecule wants to go, but it will not hit with another molecule because already under high vacuum. The mean free path is very long, a kilometer, but the distance between source and the substrate is only 1 meter. So first surface it will meet its surface itself, substrate itself. So that way you will get a perfect control. That will be evaporating molecular wise layers. That's called molecular beam epitaxy. If it is a poor vacuum in the thermal evaporation, then little bit of continuity will be there. Molecules will be going like a blobs. Okay, they are also molecules, but they are not in the atmospheric pressure. If it is atmospheric pressure, that's called gas. That's called vapor. Here it is a vapor, but molecules, and here it's only molecules in the bottom. This is called molecular beam. That is called evaporation. But both are basically evaporating from the material. One is evaporating from the solid, melted and then evaporated. Here it is only solid. Solid vapor pressure itself is good enough because background vacuum is so good, this pressure can come out. Okay, like camphor, etc. It is solid, but still you get a smell. That means what? Vapor is coming, even without melting. So this is that type of technology. And everywhere you will have analytical equipment for characterizing the things on then and there itself. And there are ways of doing it, and that is of course a big technology. ECE tech people know, and then software matching to this hardware, computer people will know. The material science and metallurgy people will definitely know what to melt, why vacuum, what is the oxidation potentials, etc. The MSc chemistry and chemical engineers definitely know how to adjust these vapors, how to make the mole fractions to realize a third material. And physical people will know what is melting point, what is boiling point, what is vapor pressure, and instrumentation people will know what is X-ray diffraction, what is the XPS, chemical compositions, etc. And then welders, mechanical engineers definitely know how to manufacture these chambers without any leaks, etc. Electrical engineers know how to pass currents and how to make plasma, etc. And electronics people will know how to make controllers for these power supplies, etc. So it's a whole game of physics, chemistry, maths, chemical engineering, mechanical engineering, electrical engineering, electronics, microelectronics, instrumentation, computer programming, and then management of all these things. If you do all that, that is called advanced materials processing and characterization. And here, the advanced materials are semiconductor and high quality pure metals, without any decomposition, proper control and proper cleanliness and proper deposition rate. That's why it's called thin film deposition. And to make it VLSI, you will get single elements for making very microelectronic circuits. And then entire thing has to be characterized. That's why thin film, vacuum deposited thin film deposition and its characterization is same as advanced materials processing and characterization. It is a name, it is a matching name. Okay, that's why I made this lecture. But there are many points I am missing definitely. If you keep these things in the Wikipedia, you will get hundreds of papers. You please go through it. Now I will give again 1 minute. How much time I have left? I think it's almost another 15-20 minutes. Okay, or half an hour.
Okay, okay, sir.
Okay, so I want again 1 minute so that all of you please read again whatever I have taught so far so that it will sink. Okay, read only memory is different, random access memory is different. If I keep on talking, you will, but you have to read also. Then there is another way of absorbing the same material. Okay. But anyway, I request organizers to freely give all these slides, share it with all the people, those who are interested in it. And if any one of you are interested, my mail ID and my WhatsApp, everything is there with Simon. So you can contact him. We will work together in your organizations to make your laboratories well, your students better, your placement of your students still better in the coming advanced national mission programs, particularly related to advanced materials. So please go through it for 1 or 2 minutes. Okay, assume that you have understood little bit about vacuum technology and evaporation, molecular beams, mean free path, and time to form monolayers and control depositions, gas inlets, mixing, and in situ analysis of physical structure like by XRD, X-ray diffraction, chemical structure by XPX or ADAX, and then continuously topology understanding by reflected high energy electron diffractions, scanning electron microscopy, which I forgot, and of course the tunneling force, tunneling spectroscopy, and then atomic force microscopy. There are several characterization techniques are coming to analyze these advanced materials and advanced devices. And I am reminding you that scanning electron microscope, that X-ray diffraction, XPS, ADAX, SCM, TM, all of them again want vacuum technology, because what is SCM? An electron beam is produced and accelerated by electric fields and bent by magnetic fields, and they're hitting and getting diffracted, and they're falling on a fluorescent screen. The scintillations are measured as an image processing, etc. So entire thing is controlled. If there is no vacuum, the molecule electron beam will not be there at all. No electron microscopy will be there. So you have to understand the characterization as well as processing require vacuum. Thin film is only one application of vacuum. There are several applications of vacuum, even in bulk, melting, casting of alloys, and even space technology, nuclear technology, because 99.9% of the journey of all our space shuttles are all under perfect vacuum. After 10 kilometers, next 1 crore kilometers is only vacuum conditions. Similarly, all the particles which are getting accelerated in our nuclear particle accelerators, etc., which is a nuclear technology, they are all under ultra high vacuum. So some other day, I will be able to talk about vacuum technology to all of you. Okay, next slide, please. So I told you already, when the temperatures of the materials, the melting points are very high, you cannot simply use thermal energy to evaporate and then make the vapor molecules and put the vacuum and then make the molecules, deposit it there and take the film, analyze it. Little energy wise, not much. So I already explained you can produce one electron beam in the top figure, U-beam deposition. The electrons are produced by a filament, hot filament by thermionic emission. you can focus on the top E-beam deposition figure. There is a filament. Please take the cursor. The filament is there. Left side of that figure, filament is there. And electrons are produced by heating it. And then just above that, there is a high voltage applied, that cap. That from there, it is accelerated. And that XXX is called a magnetic field by a permanent magnet. So magnetic field cannot accelerate any charged particles. But charged particles, when they are moving, the Lorentz force will bend them. So while electric field HV voltage is used to accelerate the electrons produced by thermionic emission, the magnetic field is used to bend these beams to focus on any desired spot of your wand. So right side, what you are seeing is a water-cooled crucible with water cooling jacket, and there is a material, blue color material, which we want to melt and deposit, and a spot of the material is heated. That raw red colored thing, that is heated, but remaining is also same material, but thermal mass is so high, one spot is melted to very high temperature, but it is so tiny spot, energy is not much, energy density is very high. So that way, that particular spot gets evaporated. It is same as our eye beam, eye surgery, LASIK surgery, laser hits, it melts a particular spot in the eye, but we don't even feel that our eye is subjected to such high temperature, because the rest of the eye is at room temperature, because it's cooled by the watering, okay, in AC room. Same thing here. So then now the green colored things are electron beams, and the black looking things are material evaporated coming out of that red thing. That material gets evaporated, but this evaporation is not totally. In thermal evaporation, earlier slides, it is melted. It is not melted here. Only in that mold, one spot is melted. Okay, it is like if you take a soldering gun on a small lead piece, big one table of lead, and try to put one, and that spot will be melted, like that. So instead of gun, you will put electron gun. Okay, this electron beam deposition, electron beam focusing is principally same in scanning electron microscopy also. There also electrons are produced, accelerated and deflected. All these things, they are actually called electromagnetic lenses. They are not called optical lenses. If it is a laser beams, you require optical lenses like glasses, prisms, like that. Whereas in electrons, for them lenses are electromagnetic fields in the form of fields in a particular direction, depending on the cross product of this product of this the charged particle velocity multiplied by the magnetic field, it will produce the force vector. Okay. So that way, the molecules are moving towards the substrate and get deposited. This is called electron beam deposition, used for costly materials. Only a small material is used to deposit, because you don't require huge material unnecessarily. It will create nonsense. Too much material, it's not a thin film, first of all, and your material is getting evaporated everywhere, and already so much costly material is gone for every small film. So from the same material, you can deposit thousands of films. The only thing is, you can put the beam, scan XYZ, by adjusting the magnetic fields and electric fields, you can make the spot at various points of that material. So this is called electron beam deposition, working with an electron source focused on a spot with the help of electric and magnetic fields, and getting deposited on the substrate for a high melting points. Bottom, there is a sputter deposition. If you cannot melt, if you cannot evaporate, if you can't do anything, then what to do is keep the material to be deposited as the high voltage electrode on top of it. From the bottom, you concentrate on sputter deposition now. So HV minus, that's called cathode. On cathode, you keep your iron or copper or whatever you want to deposit, or even ceramic. You can keep it. High voltage is subjected to that. And by either side, you keep one blue colored things, one ring of metal, so that the high voltage is focused here only. If there is a plasma discharge, it will be in this direction. It will not spread out, because there is a grounded electrode. So their electric field is less. In the actual direction, electric field is more with respect to the bottom substrate, that is also grounded. So substrate and high voltage electrode form a capacitor. On the high voltage negative electrode, you keep your material in the bulk form, and you let in some argon, AR gas. It is shown, but concentrate on only figure 2b now. So that argon gas is let in, from the right side, and vacuum pump is continuously running in the bottom, and the substrate holder is just ready to receive the film as a material and suitably supported. There is no electrical connections anywhere. Only the top there is a high voltage, and that high voltage electrode on front face of that you put your material, and now you strike a high voltage and continuously pass argon. Argon ionization potential is such that it gets discharged very fast. So when the argon gas enters between the substrate and the HV electrode capacitor, the HV electrode contains the material to be deposited also on the top. Back side is copper electrode, but front side is the material. You stick it. Then this capacitor discharges. When the discharge is there, argon molecules, the argon is ions are formed and electrons are there. Plasma. Plasma is nothing but coexistence of ions and electrons suitably confined with electric and magnetic fields. Okay. That plasma is used in Institute of Plasma Research is there in Ahmedabad. They do a lot of things for future energy applications, etc. Plasma welding, plasma processing. Here also we are using very small thing is called discharge, and sometimes when they are confined, that is called plasma. If it is little bit more, that is called arc, spark. If it is still intensity is more, current is more, voltage is also more, power is more, then it is called arc. And if it is still more high current, more voltage, then it is called lightning. So all are basically discharge phenomena containing coexistence of ions and electrons basically. Nothing more, whatever we see here in the life. Okay, coming to our point, how this is used in vacuum deposition of thin films. Now argon molecules, they will act like a machine tools. So ions, positive ions will go towards negative electrode. On negative electrode, material is sticking there, ready. This material, the argon ions will go and hit like a machine tool, and they will scratch these atoms because of momentum transfer, and that momentum molecules will be dislodged from that material and they will be ejaculated out. Where they will go? They will go to the anode. Anode is grounded. That's where the substrate is there, glass plate or silicon wafer. Now these molecules which you want to deposit from the bulk of the material, because of plasma ions heating, they are becoming molecules. The molecules will slowly settle down on the anode. They get deposited. So instead of heating the material and depositing, you are only scratching it by a ion tool. Best way of scratching is, if you cannot scratch atoms unless you have an atomic tool. You can scratch molecules with your nails, but if you want to scratch atom here, you have to have atom to scratch. So that's called argon beam. Argon ions are produced. That technique of producing argon ions in between the substrate electrodes and producing this beam to hit the ion beams to hit the negative voltage, because these are positive ions, and ejecting those molecules from there, and they get deposited. This process is called sputtering. This is exactly what we see in our day-to-day life also in lathe, etc. When you are applying momentum transfer with the machine tool, it gets chipped out. Okay, even in the grinders, wherever you are applying some mechanical force, here the machine tool is ion, and it is scratching basically. It is like what we scratch.
Okay.
Okay, next slide, please. Okay, or can you go through this slide 1 minute at least? Because if I tell something and if you don't see for yourself 1 minute, you can't get a feel of it. Just half a minute, you just go through the figures and read it 1 minute. Okay, I thought you have understood these technologies of thin film vacuum based deposition techniques. Okay, next slide, please. You are telling something? Anything problem? Hello, you just know you stopped me, no? What is any problem? Hello.
No problem, sir. No problem.
Okay.
No
So
problem, sir.
this is the last slide. Just you can go through it also. I am not saying anything. I just wanted to conclude this lecture. In fact, unless we make 100 slides, it will not be clear to you. Basically, what I have explained to you is Vacuum is a basic necessity for thin film depositions. Thin film is a basic necessity to make this two-dimensional object. That will be cut into VLSI technology to make one-dimensional, further cut into almost zero-dimensional, and dope it and etch it, and then finally package it to make semiconductor and various devices used in our cell phones, mobiles, laptops, and TVs. Second point I told you is the classification of these deposition technologies like physical vapor deposition, chemical vapor deposition, molecular beam deposition, laser-based systems, sputtering systems, depending on the style of depositing, but all of them will have vacuum in common, and all of them will have an associated processing as well as characterization facilities with the gate walls, and continuously you manufacture, you quality control, again manufacture. In an industrial scale, these are all automated operations are there. So automotive engineers are also coming into picture with electronic instrumentation fundamentals. So from the material point of view, the coatings are classified into metallic, semiconducting, optical, or polymer, or diamond-like coatings. Nowadays, diamond-like coatings are very popular. The coatings that we are seeing in our artificial, whatever we are wearing now, the decorative things, they are all coated, thin film depositions only. If you scratch it afterwards, original material will be there. That's why 1 gram gold is different from the actual gold. Okay, so it's only a top deposition layers. They are sometimes called plating if it is too thick, coating if it is somewhat less thick. It is a thin film if it is very thin. Okay, basically common name is layers, coatings. So application point of view, these are heavily used in various applications. Machine tools for wear and corrosion resistance, web coatings for thin film power capacitors used in Power Grid Corporation of India, and various BHEL, all the electrical industries use nowadays thin film capacitors. They don't use two plate capacitors. They are very bulky. Okay, we deposit in the film on a paper type thing and roll it. We have a large cross-sectional area between two electrodes when you open it. So, but the overall volume will be less. And semiconductor coatings for electronic devices, that laptops and cell phones and mobiles, and optical coatings for lenses, cameras, and solar concentrators for solar energy conversions, and packaging and decorative coatings of aluminum polymer films. See, after when you purchase any item for gift item for a marriage, you are asking them to pack it. Why? Because that thin film deposited diamond like thing are very golden type thing. It is only deposition. It is only 1 rupee. Why? It is so cheap because they are depositing thin layer. If you ask them to give a gold foil, this will be 1 lakh rupee. Okay, so thin film deposition has made sophisticated surface engineering much appealing compared to the bulk of the material is only plastic. It's only not called plastic sheet. On that you are depositing metal films or colored films so that it will look like a coated plastic paper. The plastic paper is 1 rupee and the coating is 1 rupee. That's why you are able to get 2 rupees packing materials. So different levels of sophistication are there to different products, and all of them require clean environment. That's how vacuum comes into picture. So packaging and then silicon coating for photovoltaic solar panels is coming up in a very big way. Any industry can take, any company, any college can take over at their own level. Before your college itself, you can keep it using solar panels manufactured in your college. That will be very good. So that you manufacture from a raw material of 1 lakh rupee, you manufacture 10 lakh rupee costly solar cell, solar PV arrays. You can do it. Thereby you are saving 9 lakhs. No other project is required. Your own company will give you, your own college or your own industry will give that money. You take, you spend 1 lakh rupee and 10 lakh rupee type of solar panels you create and put it on that, and you get hundreds of watts of power every day. Even there is no power without any power cut problem, and that will also act like a radiation shield so that heat will not come into your room. So several such multiple technologies you have to keep in mind, and all of them you have to think. One of them is vacuum deposited thin film technology. Other is a chemical evaporation. The other is a metallurgy, coatings, melting, casting, all the physical and chemical parameters with necessary instrumentation and software. If you are good something about everything and everything about something, then you can understand to make a device. If you want to make a device, You have to know what is lithography, what is electron beam, what is X-ray diffraction, what is this materials. And you should be expert in one of them very much so that you can take up that project. So this is what I want all of you to get benefit out of this lecture. And you can contact me, my phone number, my web, my institute number. I am working in IIT Tirupati now. Earlier I worked in IIT Kharagpur. I did my PhD also from IIT Chennai. So 3 IITs experience I had. I had seen several sophisticated equipments in IPR and BHL and Power Grid and where your applied materials in Bangalore, semiconductor manufacturers and various other companies. And so I am finding a lot of useful things in a very costly manner, which can be done by cost-effective way in indigenous. Now government of India is giving a lot of money to take different mission programs. For solar mission is there, semiconductor mission program is there, and then various space technology programs are there. Nuclear everywhere requires advanced materials processing. New materials you can manufacture in bulk. Understand? Then tell if you can finally process, you will get this application. But basic physics I have done, basic chemistry I have done. I can do the chemical engineering to make it large scale production of the material. I can do the metallurgical engineering to melt it properly, cast it in a uniform ingots, or you can increase the strength. I can do the electronic engineering by making thin film materials and understand the motion of electrons and holes and make different circuits. And I can program it so that this mathematics is understood to the physical language by the semiconducting circuits. That if you understand, that's also very good. And the artificial intelligence is required for it, and through a machine language. If you do that AML into this modern day electronics, which has got a base of thin film deposition under vacuum technology, made out of advanced materials, continuously being processed and characterized, you are the master. And at your own level, you can take up with your own budget, and you will be able to do it. If you do one success, people will come. Not only the fund givers, but industries will come to you if you develop any particular technology of so many things. You should know one thing in thoroughly and everything something. So with this idea, the vacuum deposited thin film deposition is going to play a very important role in the coming days in electronics, electrical engineering, chemical engineering, even in food processing, even in decorative pieces, and all the devices that we are using in the day-to-day life. So thank you very much for your kind hearing. I'm sure I would have told unnecessarily a little more this way, that way, but that's a part of the teaching. Okay. Thank you very much. So my side is over.
Okay, sir. Now it, sir, participant asking some questions, sir.
Please.
What precautions should be taken while working with laser beam deposition and toxic materials?
Repeat the question.
What precautions should be taken while working with laser beam deposition and toxic materials?
And fax material. What is it?
Toxic materials.
Toxic materials. Yeah. Sure. See, if it is a vacuum deposition, typical laser beams, first of all, you should know the laser technology. And lasers are collimated beams, so that intensity is very high. There is an optical window. Through that, it enters into the chamber. Laser can cross the material chamber wall and go to the other side if there is an optical window. So vacuum chamber should have an optical window, and your laser beam should be focused so that it will fall without any spread directly onto your material. That is the first precaution you have to take. Collimation and aligning the laser beam to the substrate, to the material, not the substrate, to the material. Okay, there is no high voltage, low voltage. Directly laser beam is falling. Then these things are coming, whatever that is coming. If it is a toxic material, you have to take full care of it even when you are introducing, because material you are taken, you are having thin film of the same material. So whatever precautions that you are taking in handling the initial material is same as processed thin film also. Only during the process they have formed as a flue of gases, because initially a solid poison or a vapor poison is same. Okay, but molecules. Apart from that, air nitrogen molecules are also there. So you have to reduce sometimes some molecules under oxygen, they catch fire, because already there may be some fuels. These toxic materials are also having fuel type of behavior. And if oxygen is there, they may burn and they may create accident. So you have to continuously analyze the chemical residual gas whatever is there, not much. Even though oxygen is there, composition is not much. The actual vapor molecules which are coming, toxic molecules, the density is not that much that they will not have a cooperative blasting. They will only get deposited. And in the process, whatever excess things are there, including impurities, they are continuously scavenged by the rotary pumps or vacuum pumps. While exhaust of the vacuum pumps, you should leave it to the outside or some catalyst which will again neutralize these things before you exhaust them. So exhaust management is the most important precaution when you are trying to evacuate things and take the plasma assisted deposition, laser assisted deposition. So exhaust level, you have to take care of filters and properly, and the room should be ventilated properly, the laser beam should be focused properly, and the control of the residual gas analysis should be done. That precaution you should take. And if any particular composition is going on, switch off the process, etc. And there may be here and there some high voltages associated with the laser beam creation, so you should see to that you should not touch here and there, and there should not be moisture around that much, so that moisture will form a unnecessarily a layer on the glass window and laser beam gets deflected. So these are the precautions you have to use. And chemically, you have to take care of all the precautions. Normally, the materials people, the suppliers will tell, these are the toxic materials, you should not smell. The person should hold with a hood so that you will have your own oxygen. Only the material, even if it is coming from the chamber, from this and device and goes to the vacuum pump, goes out. But you should not leave it to your neighbor. Then they will put the soot. So you have to put it through a bubbler or a water, something, so that it gets neutralized. Or you should catch it in a catch pot with a suitable absorbing materials are coming now. Is a very good question. And in fact, these are the precautions. I think it has come from a brain who knows physics and chemistry both, and also knows little bit instrumentation. Very good question. I hope you got some idea.
Finally, now it's vote of thanks, sir. So, participant asking only one question, sir.
Yes.
Now it's vote of thanks, sir. For me only. On behalf of H&S department, today I take this opportunity to put all my gratitude in the form of words. First of all, I would like to thank our today eminent speaker, Professor Vasudeva Rao Garu, for accepting our request and for giving such a wonderful presentation on vacuum-based thin film deposition technologies and making even meaningful and interesting. Thank you very much, sir. I would like to express our profound gratitude to our Principal, Dr. Sayed Surya Madam, for her constant support and encouragement throughout the program. Thank you, Madam. I would like to extend my heartfelt thanks to our beloved correspondent, Srimati V.K. Padmavatama Madam, and our Director, Srimati V.K. Srivani Madam, who has initiated us to this program and her continuous support right from these inceptions. Thank you, Madam. I would like to express my gratitude to our Managing Director, Sri Raghunath Reddy Sir. Thank you, sir, and supporting us, guiding us in right way. My heartfelt thanks to our convener, Dr. Haripriya Madam, and her entire team, Dr. Jansi Rani Madam, Mr. Jayprakash, Mrs. Srimas Suman Gopinath, and Engineer Madam for this continuous support in making third day of this FDP successful. A big thank to you, Noor sir and Nagendra sir, who is backbone of this online session by providing technical support. Thank you, sir. Finally, at the end of the session, I would like to thank you all the participants of this FDP for their glorious presence. Thank you, everyone.
I also thank everyone, and I thank very much for the GATE Institute of Technology for giving me this opportunity, the management people. And also I thank the organizers of this conference. They very nicely organized things. The topics are very nice looking. Thank you all for giving me this opportunity.
Thank you, sir.
Thank you. We will see again some other day. Is it okay? Shall I close it now?
Okay, sir. Is it okay? Close your notes.
Yeah, please. Thank you.
Thank you, sir.